Hello everyone, welcome to my channel Physics with Bhatt. To learn concepts of physics, subscribe this channel and press the bell icon button to get notified for every new video lecture.
Good morning, dear students. This is Bhatt once again with you with the new video lecture. I have been doing the series of video lecture for wave optics. Today I brought a new topic for you, that is width of the fringes and intensity in diffraction. In the last video lecture we discussed about the diffraction at single slit. Find the expression for the positions of bright and dark fringes obtained on the screen. Today we will find the width of fringes and intensity in diffraction. Let's see the diagram for the fringes obtained in diffraction. In this diagram you can see this is single slit, a plane wavefront incidenting on the single slit. After diffraction, the fringe pattern is obtained on the screen, that is also visible here. Center of screen is bright. After that, alternate dark and bright fringes are seen. This is central bright fringe, then dark, then bright, then dark, then bright. It is above the center, and below the center also we have dark, bright fringes. So, in that way you can see the alternate dark and bright fringes are seen after the central bright fringe. So, center of the screen is bright. After that, alternate dark and bright fringes are seen on the screen. One more important thing you should understand here, that the every dark fringe is between two consecutive bright fringes. Likewise, every bright fringe is between two consecutive dark fringes. Just see here, this is the bright fringe lying between these two dark, and this is the dark fringe lying between two consecutive bright fringes. So, now we will find the width of these fringes. So, let us begin with the width of dark fringe first. Every dark fringe is lying between two consecutive bright fringes. Therefore, the separation between two consecutive bright fringes will be equal to width of the dark fringe. To find this mathematically, we will find the separation between two consecutive bright fringes. Let the two consecutive bright fringes are n and n plus 1. So, the width of dark fringe beta is equal to y dash n plus 1 minus y dash n. So, beta is equal to 2 n plus 1 lambda d upon 2d minus 2 n plus 1 lambda d upon 2d. If you open the bracket, then beta is equal to 2 n plus 2 plus 1 lambda d upon 2d minus 2 n plus 1 lambda d upon 2d as it is. Now, lambda d upon 2d is common. So, beta is equal to lambda d upon 2d. Inside the bracket, 2 n plus 2 plus 1 minus 2 n minus 1. So, beta is equal to 2 n cancel, 1 is also cancelled. So, beta is equal to lambda d upon 2d into 2 is cancelled. So, lambda d upon d. Therefore, beta is equal to lambda d upon d. So, this is the width of dark fringe and it is lambda d upon d, where lambda is wavelength of light used, d is distance of screen and small d is the width of single slit used. Now, move towards the width of bright fringes. So, let us see how to find the width of bright fringes. We know every bright fringe is lying between two consecutive dark fringes. Therefore, the separation between two consecutive dark fringes will be equal to width of the bright fringe. How to find this width? We will just take again the two consecutive numbers of fringes. Let the number is n and n plus 1. So, we will find the separation between two fringes. So, beta dash is equal to y n plus 1 minus y n. Beta dash is equal to n plus 1 lambda d upon d minus n lambda d upon d. These are the positions of n plus 1 and n fringe. So, beta dash is equal to lambda d upon d common, n plus 1 minus n and n cancel. So, beta dash is equal to lambda d upon d into 1, that is beta dash is equal to lambda d upon d. So, this is the width of bright fringe, every bright fringe will be having the width. So, this formula is similar to the formula obtained for the width of dark fringes. Therefore, we can say beta dash is equal to beta is equal to lambda d upon d. So, width of both bright and dark fringes is same, that is lambda d upon d. Now, its turn for the central bright fringe. Let us see how to find the width of central bright fringe. The central bright fringe is lying between first dark on either side of the screen. We had seen in the diagram that above the central bright fringe there is dark fringe, and below the central bright fringe also there is dark fringe, and that number is 1. So, distance between these two first dark fringes on both the sides is equal to width of the central bright fringe. So, central bright fringe is between first dark on either side of the center of the screen. Therefore, the width of central bright fringe beta node is equal to twice y1. y1 is equal to lambda d upon d, since the position of dark fringe is given by and lambda d upon d. So, beta is equal to twice lambda d upon d. It is clear that the width of beta node is equal to twice of beta is equal to twice of beta dash. That is, the width of central bright fringe is double the width of other fringes. So, in that way we discussed about the width of dark fringe, bright fringe and central bright fringe. Now, it is the turn for intensity of the fringes. We had discussed about the intensity of fringes in interference, and there we found that intensity of all the fringes is same. So, let us see how the intensity is interpreted here in diffraction at single slit. Let us see the diagram, that is the intensity curve for the single slit diffraction. You can see a big peak in the middle of this diagram, that is related to point 0. This point 0 is the center of the screen, and this peak is corresponding to the central bright fringe. The central bright fringe is of maximum intensity, and other fringes are having low intensity in comparison to the central bright fringe. You can see here are two scales on the x axis representing the position and phase difference. At position lambda d upon d, first dark is obtained. At position 2 lambda d upon d, second dark is obtained. At position 3 lambda d upon d, third dark is obtained, and so on. In between you can see the positions of bright fringes also. The other scale is with phase difference. For the first dark, phase difference is pi, then 2 pi, then 3 pi, and so on. So, at these positions and phase differences, we can see the intensity of the fringe is obtained. So, central bright fringe is of maximum intensity. After that, the intensity of other fringes decreases, as shown in here in the diagram. The question arises, why the intensity is abruptly decreased after the central bright fringe? The reason behind is very simple. If you could recall, in the last video lecture we had discussed how the bright fringes are formed, and for the purpose we had divided the wavefront into 3 parts, 5 parts, 7 parts, and so on. One fraction of those division was responsible for the formation of bright fringes. So, we can say only a fraction of wavefront is producing the bright fringes. Therefore, intensity of the bright fringes decreases as we move away from the center of the screen. So, that you can see here also, the intensity of central bright fringe is maximum. After that, it is decreased abruptly and then decreasing gradually. So, the reason is very simple, the fraction of wavefront is producing brightness. I hope this will help you in understanding the concept of diffraction more effectively. We will meet very soon in the next video lecture. Till then, keep watching, keep learning.